Good evening, all.
Good evening, madam.
Yeah. Just to avoid echo, can you please mute? Okay, thank you. So, welcome back to live discussion session on soil mechanics and geotechnical engineering NPTEL course. We'll wait for 2 more minutes and then we'll start the session. I'll share my screen. Hope this is visible to everyone. Okay. So, so let's start today's discussion session. So last week, professor was discussing about compaction, critical hydraulic gradient, effective stress, total stress, all these in the lecture videos. So I hope all of you have gone through those lecture videos. So here is our first question for today. A soil deposit has a void ratio of 1 if the void ratio is reduced to zero point 0.6 by compaction. The percentage volume loss is. So, we are given a soil deposit with an initial void ratio of 1, and later on, when we compacted the soil, the void ratio have reduced to zero point 0.6. So, we have to determine the percentage volume loss. So, can you please solve it and tell me the answer? You can put in the chat box. So we need to determine percentage volume loss, initial void ratio as well as void ratio after compaction is provided. Option A 10 percentage, option B 20 percentage, option C 30 percentage, and option D 40 percentage. I'll wait for 2 minutes, then I'll explain how to solve this. Okay, I have got one answer as option B 20 percentage. Any other answer? All right, let's see how to solve this. So answer is option B 20 percentage. So we are given that initial void ratio is 1 and void ratio after compaction is zero point 0.6. Now what is the equation for void ratio? It is volume of voids by volume of solids. In all the previous discussion sessions, we have seen that equation, that is E is equal to VV by VS. So it is given that VV by VS is equal to 1 initially. What does that mean? Volume of voids is equal to volume of solids, or total volume, which is the sum of volume of solids plus volume of voids, can be written as 2 times volume of solids, because volume of voids is same as volume of solids. Clear? Now, after compaction, the void ratio have become zero point 0.6. That means VV by Vs has become zero point 0.6, or v, VV is equal to zero point 0.6 Vs. VV is equal to zero point 0.6 Vs. That means total volume becomes 1.6 Vs. So initially our total volume was 2 Vs, and then after compaction we got the total volume as 1.6 Vs. Now, in order to calculate percentage volume loss, we should deduct this, like initial volume minus final volume, and then divide by initial volume. So percentage volume loss is initial volume minus final volume divided by initial volume into 100. Now it becomes 2 Vs minus 1.6 Vs divided by 2 Vs into 100. So all the Vs can be took outside from the numerator and can be cancelled with the denominator. So we will get it as 20 percentage. Is that clear? How to solve this question? Is that clear? All right. So let me move on to the next question. So the second question is, the in situ void ratio of a granular soil deposit is zero point 0.5. The maximum and minimum void ratios of the soil are determined to be 0.75 and 0.35. Specific gravity of this granular soil deposit is 2.67, and unit weight of water is 9.81 kilonewton per meter cube. We need to determine the relative compaction in percentage of the deposit. Option A 62.5, option B 77.1, option C 85.7, and option D 90. So we are given in situ void ratio or natural void ratio, maximum void ratio, and minimum void ratio. We need to determine relative compaction. Relative compaction. So which is the correct option? So there is a direct relationship between relative compaction and the unit weights. Okay, in the chat box, I have got one answer as option D. Any other answer? I think 4 people are there. So can others also please do the problem and put the answer in the chat box? Or if you need extra time, that also we can, like, you can please mention it in the chat box. All right, let's see how to solve this. So the option is, correct option is option B, 90 percentage. So we are given that in situ void ratio of the granular soil deposit is zero point 0.5. Maximum, sorry, maximum void ratio of the soil is 0.75 and minimum void ratio is 0.35. Also, specific gravity and unit weight of water is given. So, by equation for relative compaction, R is equal to gamma D in C2 by gamma D max into 100. Now we don't know gamma D in C2 or gamma D max, but instead we have the void ratios E max, E minimum, and E in C2. So, how to determine gamma D in C2? It is equal to G gamma W by 1 plus E, corresponding E. That is gamma dry. Dry unit weight equation is G gamma W by 1 plus E. When we need the dry unit weight of in situ soil or that at the site soil, we use in situ void ratio. So it becomes G gamma W by 1 plus E in situ. Similarly, when we need gamma D max, we need to use minimum void ratio. So, first calculating gamma D in situ, we'll get it as 17.462. Now coming to gamma D max, it becomes G gamma W by 1 plus E minimum, which we get it as 19.402. So dividing them and multiplying with 100, we get relative compaction as 90 percentage. So relative compaction is the ratio of gamma D in situ to gamma D max expressed as percentage. Okay, let's see the next question. This question is somewhat similar to a question that we had done in our second live discussion session. So, a 1220-meter long embankment of width 7.5 meter and zero point 0.8 meter compacted thickness is to be constructed in a part of roadway project. Construction specifications require the soil to be compacted to moisture content of 19.1 percentage, achieving a dry unit weight of 16.4 kilonewton per meter cube. Soil is to be excavated from a borrow pit where soil has a moisture content of 15.7 percentage and bulk unit weight of 17.25 kilonewton per meter cube. The volume of soil to be excavated from borrow pit. So, say a similar question we had done in our previous discussion session. So that time itself we had seen the only concept we need to consider here is the fact that volume of soil solids excavated from the borrow pit will be equal to the volume of soil solids in the embankment. So can you please solve it? So which is the correct option? Okay, I have got one answer as option D in the chat box. Only one student is giving the answers. All right. Okay, so Let's see how to solve this anyway. So the correct option is option B. So here we are given with the length, width and the compacted thickness of the embankment, the natural moisture content in the borrow pit as well as the required moisture content in the embankment, specific gravity, bulk unit weight of soil in the pit and dry unit weight that is required in the embankment, and unit weight of water. So all these values are given. Now, in order to calculate the volume required to be excavated from the pit, the concept we need to consider is volume of solids excavated from the pit will be equal to volume of solids in embankment. That is, and also we know that volume of solids is equal to total volume minus volume of voids, because total volume is the summation of volume of solids and volume of voids. So from the void ratio equation we have E is equal to VV by Vs, or we can write VV as volume of voids as volume of solids into void ratio. Substituting this particular equation back here, what will we get? We get volume of solids as V minus VSE, or Vs, volume of solids can be written as V by 1 plus E. Now, this particular fraction will be equal for both pit and embankment case. That is, volume of pit or volume excavated from pit by 1 plus void ratio in the pit will be equal to volume of embankment by 1 plus E embankment. Now, for determining volume of embankment, we are given with length, breadth as well as compacted thickness of the embankment. So, multiplying them, we'll get the volume of embankment. We know that dry unit weight and bulk unit weight are given by the equations G gamma W by 1 plus E and G gamma W into 1 plus W by 1 plus E respectively. So, substituting for void ratio pit and void ratio in embankment respectively in the bulk unit weight and dry unit weight equations, we get void ratio of the soil in the pit is equal to G gamma W into 1 plus moisture content in the pit divided by bulk unit weight minus 1. So we'll get it as 0.763. In a similar manner, when we calculate E embankment from the dry unit weight equation, because the unit weight given here for embankment is dry unit weight, we'll get it as 0.603. Now substituting back in that equation, volume to be excavated becomes equal to volume of embankment by 1 plus E embankment into 1 plus E pit, which we get as 8050.63 meter cubes. So the nearest option is option B. All right. So the next question is, optimum moisture content of a soil is 17 percentage.
Excuse me, madam.
Yes.
Can we go to previous slide, madam?
Yes, 1 second. Yeah.
Madam, here, what is the need of finding a void ratio, madam? Why not directly density you can use? Density into volume is equal to density into volume formula. You can use it, na, madam.
I didn't get that.
Madam, density is equal to mass by volume.
Yes.
Mass of the solids is a constant here before compaction, after
Yes, we can
compaction.
consider either volume or the mass.
Yeah, madam. Then we have a direct formula. Density is given.
Yes.
Volume also, one of the volume of the fill is given.
Yes,
So
we can calculate it.
density into volume is equal to density into volume.
Yes, actually, like for a single question we can find it through different ways, right?
Yes, madam.
So
Yes, madam.
like that also we can find, like by considering that mass is a constant also we can do the problem, or volume.
Because this example, unit weight is not essential to use, and G also no need of using.
Yes, just because they have given that in the question, so I was explaining using that.
Oh,
That's it. But we
yes.
can do the other way also. Both
Okay,
the.
madam. Fine. Thank you, madam.
Okay. So moving on to the next question. The optimum moisture content of a soil is 17 percentage and its maximum dry density is 16.7 kilonewton per meter cube. The specific gravity of soil is 2.7. Then we need to determine the theoretical dry density in kilonewton per meter cube at optimum moisture content corresponding to zero air voids. They have given unit weight of water as 9.81 kilonewton per meter cube. Option A is 16.525, option B 14.726, option C 18.154, option D 19.235. So we are given the optimum moisture content, maximum dry density, specific gravity. We need to determine theoretical dry density. So which is the correct option? We need to determine gamma D theoretical at the given optimum moisture content of 17 percentage corresponding to zero air voids. Maximum dry density is also given. Okay, I've got one answer in the chat box as option C. Any other answer? Alright, so let's see how to solve this. Correct answer is option C. So we are given the optimum moisture content of soil as 17 percentage or 0.17, maximum dry density as 16.7 kilonewton per meter cube, specific gravity of soil as 2.7, and unit weight of water as 9.81 kilonewton per meter cube. Now, the equation for gamma D theoretical is G gamma W by 1 plus GW. This comes from the equation G gamma W by 1 plus E. And here it is mentioned that zero air voids corresponding to zero air voids. That means whole voids are filled with water or it is saturated. So S becomes 1 and then E becomes GW. Because in the earlier uh, discussions we have seen ES is equal to GW, that equation we have. So from that we have this gamma D theoretical equation as G gamma W by 1 plus GW. Substituting the values we get gamma D theoretical is equal to 18.154. 18.154 gamma D theoretical. Is that clear? Okay. So next question. But
Madam, 1 second, madam.
yes.
What is the difference between that maximum dry density and this theoretical dry density, madam? Both, I think, both are not same.
No.
What do you mean? The theoretical dry density is nothing but maximum dry density. So then again, what is that maximum dry density?
One second. Can you come up with the question again?
See, in the question, theoretical maximum dry density is given,
Yes.
but theoretical dry density itself, the maximum dry density.
They have asked for a theoretical dry density corresponding to zero air voids, right?
That is the maximum dry density possible for any soil sample.
Okay, actually, the thing is, zero air voids, that concept. One second.
You got my point, madam?
You're asking whether maximum dry density is same as theoretical dry density, or
Yeah, maximum dry density for any soil sample is nothing but
hmm.
theoretical dry density itself, maximum dry density. That is the possible value. Maximum possible value is theoretical dry density only because zero air voids. Then what do you mean by that question in the question given maximum dry density?
Okay. The thing is, so the maximum dry density and theoretical um, dry density, the difference is that in the case of theoretical dry density, there we are considering that zero air void ratio line and all. You remember when we do that compaction test and all?
Yeah.
Yes. So maximum dry density, what does that mean? It is the dry density of the soil that corresponds to the optimum moisture content, right?
Yeah, that's what. That itself the maximum dry density.
Yes, that is the maximum dry density. Now, what
Then
they yes, yes, what you were telling?
Madam,
Yes,
can I interfere, madam?
sure, sure. That's what it is called discussion. No, everyone can.
Yeah, with your permission, I will answer for this question,
Sure,
madam.
sure.
At maximum dry density, always air voids are present.
Yes, that is what I was trying to tell. Yeah, please continue.
Anywhere in the laboratory compaction curve, air voids will be present.
Yes,
Air voids are minimum only at the maximum dry density.
yes.
But at theoretical dry density, air voids are completely zero.
Yes,
Anywhere on the theoretical dry density, air voids are completely zero.
yes.
so which is imaginary at
Yes,
the
sir. Yes, sir.
Theoretical is all the theoretical values. That's why we call them as theoretical. It's we
okay,
are
practically it is not possible.
no, even if you
Okay.
compact with the what you call all the high techniques available, some minor voids will be filled with air. It is not possible to expel that air out. But
Mm-hmm. Okay.
so that we'll mention it as, but that is the maximum dry density that is attainable. What you told is correct. That is the maximum that we can attain. This theoretical remains theoretical. It's not practically possible. It's theoretical alone. That's why we are
Okay.
reading it from that one graph that we draw. Then we make a theoretical zero air voids line for the compaction test.
Mm-hmm. Yes, ma'am.
Yeah.
Okay,
Even
okay.
even even if you go for modified compaction test also, anywhere on the compaction curve, air voids will be present.
Yeah. If you plot
Only
that both curves, you can see that like it is it won't touch that zero air void line. It will be still above it. It will be still above our graph.
Yes, ma'am. Okay, madam.
Oh.
Okay.
thank you, madam. Sorry for
No, no, thank you. Actually, now it have been like exactly become a live discussion.
thank
Earlier,
you, madam.
only I was talking and I was explaining. There was no discussion. Now discussion is happening.
Thank you, madam.
Yeah, thank you. So we'll move on to the next question. The relationship between the specific gravity of sand and the hydraulic gradient to initiate quicksand condition in the sand layer having porosity of 40 percentage is. So we have the specific gravity of sand as G, hydraulic gradient I. So in order to initiate a quicksand condition for a sand layer with porosity 40 percentage, which of the following is the correct equation or correct expression? Uh, you can start with considering the quicksand condition, the criteria for quicksand condition, and then arrive in the equation. Okay, I have got one answer as option C. Any other answer? Yes, I have got one more answer as option C. All right, let's see how to solve this. So correct option is option C. We are given that porosity N is equal to 40 percentage or zero point 0.4. We know that in order to have the quicksand condition, critical hydraulic gradient should prevail. Only then quicksand condition will happen. And the equation for critical hydraulic gradient is given by G minus 1 by 1 plus E. Now, we know to determine void ratio E from porosity N, that is E is equal to N by 1 minus N. So, we will get it as 0.67. Back substituting this value in the equation for critical hydraulic gradient, we'll get it as G minus 1 by 1 plus 0.67. Rearranging this particular equation, we'll get it as G is equal to 1.67 IC plus 1. Is that clear? Okay. So here is our next question. A seepage flow condition is shown in figure. The saturated unit weight of the soil is gamma sat is equal to 18 kilonewton per meter cube. Using unit weight of water as 9.81 kilonewton per meter cube, the effective vertical stress expressed in kilonewton per meter cube on plane XX is. So we need to determine the effective vertical stress on the plane XX. So we know that effective vertical stress is equal to total stress minus pore water pressure. So first determine total stress, then determine the pore water pressure, and then effective vertical stress. Okay, I have got one answer as option B. Okay, let's see how to solve it. So the correct option is option B. So we are given with saturated unit weight of the soil and unit weight of water. We know that effective stress is equal to total stress sigma minus pore water pressure. Now, the total stress at Xx is equal to the stress due to the water and the saturated soil. So water is there for 5-meter height and soil for 4 meters. Substituting, we get total stress as 121.05. Now pore water pressure is the pressure exerted by the water in the pores. So gamma W into total height minus that hydraulic gradient, because here we have this much, 4 plus 1 plus 4 we have water, sorry, 4 plus 1 plus 4 we have water, and also this particular height there is loss happening, energy loss happening. So pore water pressure becomes 56.898, substituting the values. Then effective stress is given by total stress minus pore water pressure. So it becomes 64.152 kilonewton per meter square. All right. Coming to the next question. The subsoil at a site consists of 2-meter thick layer of clay, which is underlined by a deep sand layer. Groundwater level is at 3 meter below ground level. Unit weight of clay is 18 kilonewton per meter cube. Unit weight of sand above and below the water table is 17.5 and 19.2 kilonewton per meter cube respectively. The total stress and effective stress at a depth of 5 meter below the ground level are. So here we are given a soil strata, which is a mixture of clay underlain by sand layer. 2-meter clay layer is there. Below that we have sand layer. And water table is at 3 meter below ground level. Unit weight of all the layers are given. We need to determine total stress and then effective stress. Equations are similar. So the correct answer is option A. We are given that unit weight of clay, unit weight of sand above water table, below water table, and unit of weight of water. All these values are given. So this is the pictorial representation of the data that is given in the question. Ground level is there. 3 meter below that, we have water table. First 2 meter we have clay, and below that it is sand. Our concern is 5 meter below the ground level. Okay. So what will be the total stress? Total stress is the stress due to clay sand above the water table and sand below the water table. That means 2 into 18, that is unit weight of clay, plus 1 meter sand above the water table. So 1 into 17.5 plus 2 meter sand below the water table. So total stress at 5 meter becomes 91.9 kilonewton per meter square. Now effective stress is equal to total stress minus pore water pressure. So pore water pressure is equal to unit weight of water into depth up to which the water is there. That is 2 meter. So 91.9 minus gamma W into 2. So subtracting total stress, sorry, pore water pressure from the total stress, we get effective stress. Is that clear? All right. So here is the next question. In a 6-meter thick stratum of fine sand having submerged density 11 kilonewton per meter cube, quicksand condition occurred at a depth of 4.2 meter of excavation. The depth of lowering of water table required for making an excavation 5 meter deep is. So initially at a depth of 4.2 meter of excavation, like an excavation was done up to a depth of 4.2 and quicksand condition occurred. Now if we need to increase the excavation depth to 5 meter, how much should we lower the groundwater table? How much should we lower the groundwater table? Okay, I have got one answer as option B. Let's see. Yes, correct answer is option B. So how to solve that? We are given the thickness of the fine sand stratum is 6 meter. Submerged density is 11 and depth at which quicksand condition occurred was 4.2. So we were able to excavate only till 4.2. Then quicksand condition occurred. Now let the initial groundwater table depth be x meter as shown in the figure from the ground surface. Then what will be the total upward pore water pressure on the sand layer at the bottom of excavation? It will be unit weight of water into depth of water, that is 6 minus x, this much. Below this dot dashed line, that is the height of water, that is 6 minus x. We don't know the initial depth of groundwater table, so let it be x. Now Total downward force at the bottom of excavation. Total downward force at the bottom of excavation is the weight exerted by the soil above. That is saturated soil because it is below groundwater table. So gamma sat into depth of the soil mass, that is 6 minus 4.2, this much area. Now gamma saturated is not given, but gamma submerged is given in the equation problem. So we know that gamma submerged is gamma saturated minus gamma W. So using that equation, gamma saturated becomes gamma submerged plus gamma W, and we'll get total downward force at the bottom of excavation as 37.458 kilonewton per meter square. Now, for quicksand condition to occur, both upward force and downward force should be equal. That means total upward pore water pressure is equal to total downward force. So equating those equations, we get x is equal to 2.182 meters below the ground surface. So initially the water table is at a depth of 2.18 meters below the ground surface. Now, if we are lowering the water table, say to y, initial water table is x and we are lowering it to y, the same condition occurs for the quicksand. That is gamma W into 6 minus y, that is the pore water pressure in the upward direction, will be equal to the downward force exerted by the weight of the soil. So we get y, or the depth, to be lowered from the ground surface as 3.879, and comparing with the initial water table, we get it as 1.697. So what we need to consider is the fact that during quicksand condition, the upward pore water pressure will be equal to the downward force exerted by the weight of the soil. So we will get the amount or depth by which water table is to be lowered in order to make an excavation of 5 meter. Okay. Yes. So next question. In a deposit of fine sand layer, water table is at 4 meter below the ground surface. But the sand up to height of 1.5 meter above the water table is saturated by capillary rise. The sand above this height, that is above this 1.5, may be considered as dry. For the sand, specific gravity is 2.7 and porosity is 35%. Unit weight of water is 9.81 kilonewton per meter cube. Effective stress at a depth of 8 meter below the ground surface is. So, we are given a soil strata. It's a sand layer with water table at 4 meter below the ground surface. But 1.5 meter thickness of the sand layer above this water table is also saturated by means of capillary rise. The remaining sand layer above 1.5 meter and the ground surface, that is lying between this 1.5 meter level and the ground surface, can be considered dry. So there is a dry layer sand immediately below the ground level. Then we have saturated sand, that is saturated by means of capillary rise, and then we have the water table, and below we have the fully saturated sand. So we need to determine the effective stress at a depth of 8 meter below the ground surface. Again, as in the previous questions, we need to determine total stress and pore water pressure, then deduct pore water pressure from effective stress, total stress to get effective stress. So first determine total stress, then pore water pressure. Only thing you have to keep in mind is some layer of sand above the water table is also saturated by capillary rise. So here porosity and specific gravity is given. The other values you need to calculate from the equations. Gamma saturated, gamma D, all these values you need to calculate. Okay, let's see how to solve this. So the correct option is option B, 117.3. So we are given the depth of water table below ground level, depth of sand saturated by capillary rise, depth of dry sand, specific gravity of sand, porosity, and unit weight of water. So total stress at 8 meter will be 2.5 meter dry sand is there. So gamma D into 2.5 plus gamma sat into 1.5, that is for the sand saturated by capillary rise, and the remaining 4 meter gamma sat. So all these values are there, but we don't know gamma D and gamma sat. So for determining gamma saturated and dry unit weight, we know porosity and specific gravity. So gamma D is G gamma W by 1 plus E, and gamma saturated is G plus E gamma W by 1 plus E. Now we'll determine E from porosity. That is N by 1 minus N, which is equal to 0.538. Substituting, we have gamma D is equal to 17.22 kilonewton per meter cube. Saturated unit weight 20.65 kilonewton per meter cube, and then substituting in the equation, total stress becomes 156.625 kilonewton per meter square. Now effective stress is total stress minus pore water pressure. The pore water pressure is 9.81 into 4. So effective stress becomes 117.385 kilonewton per meter square. Is that clear? The equations are similar to that we used in the previous questions. Only difference is that here the unit weights are not directly given. We have to determine that from the given values of porosity and specific gravity. Okay. So with this, uh, questions for today's discussion is completed. So if there are any doubts,
Excuse me, madam.
yes.
Madam, in your slides, what is the slide, current slide we are using?
Sorry.
Present in your PPT presentation,
Yes.
what is the last slide number we have used, madam? 28 or
Last slide number 29.
do you have any questions beyond that, madam?
No, no, no.
No, okay. Because if there is any one or two questions,
Yes, yes.
if you pass, it will record so that we can make our own homework.
No, actually, I have completed all.
Okay, madam. Done,
Uh,
madam.
all like in total 10 questions were there, but I have combined like two questions in a single one. Like I think here in the seventh question, yes, this question was actually two. Total stress in a separate question, and for the same data, effective stress in another question. So just for
Okay,
the
okay.
easiness, I had combined it together.
Yeah, next time, if possible, add one or two questions, madam, so that we will do as a homework.
Oh, sure, sure. That I'll do. Yes, sure.
Thank you, madam.
Yeah. Okay, then. So,
Madam, in the previous question just now you shown, na, show me
yes,
that
yes.
question, madam.
Yes, one second.
So,
Yes. Yeah, this question, ninth question, right? Last question.
right, this
Yes.
question, madam.
Yeah.
Here the capillary rise is not, we have not considered that capillary rise and capillary issue.
No, we have considered here depth of sand saturated by capillary rise is 1.5 meter. So
Okay,
that we have multiplied with saturated unit weight only.
okay, but, okay, okay.
Either you can combine these two terms also, but just for like explaining it, I had separated these two
Mhm.
terms.
Okay, okay. Suppose if the effective stress, calculate the effective stress below 2.5 meters level
Okay, below
from the ground
2.5.
level.
Okay.
Calculate the effective stress 2.5 meters below the ground level.
Yes.
Then capillarity issue will come, I think, madam.
Then
The
also with
capillary issue.
yes. Okay. Then what happens is below at the like if we are calculating at 2.5 means full like only the we'll consider the soil only above the considered plane, right? When we are
Effective stress at
uh,
madam,
uh,
effective stress at 2.5 meters below the ground level. That I want.
yes, that means all the soil in that particular location you're considering is dry sand.
Okay.
So at that point, what will be the stress coming up only with the dry sand? So only this term will be there 2.5 into gamma d in
No,
the
no, no,
total stress.
madam. That at that time, the negative capillary pressure also we need to consider, and then that you whatever you are saying that 2.5 to gamma d minus of that minus we have to consider the effective stress at that time. It will change, madam. Capillary, because of the capillary rise, the effective stress will be increases. If we consider at 2.5 meters below the ground level, if you consider the effective stress, that is 2.5 into gamma d
Huh.
plus this negative capillary pressure, we have to consider that minus of minus.
But the sand that is saturated by capillary rise is below the level.
Yeah, below the level, but at the 2.5 level means that at that interface, na,
Yeah, exactly.
at that interface, pore water pressure, negative pore water pressure will be there. 1.5 gamma W. 1.5 gamma W at that at the junction, and 1.5 gamma W will be there.
That I'm not sure. I'll check and tell you during the next discussion because I'm not sure. So I can't tell
Oh,
like that.
Madam,
okay.
I will
You confirm it, man. Confirm
Okay,
it.
sure, sure. I'll confirm and I'll explain that.
Same. The question is at 2.5
Yes, I
meters.
understood.
I
I
want to
understood the
calculate the
question.
effective.
Yes, yes, I understood the question. With the same question, you want to calculate the effective stress at the 2.5 meter. That is the
Exact.
meeting point of this capillary rise, saturated sand, and the dry sand.
Exactly, madam.
Yes,
Exactly.
yes. Okay,
Madam,
yes.
can I answer for that?
Yeah, sure.
Uh, at 1.25 meter from ground level, total stress will not change. Whatever we had done calculation, it is similar.
Total stress same.
Yeah, no, not the same. Procedure is same. Total stress at 2.5 meter is equal to 17.21. That is gamma dry into 2.5 meter
Yeah.
minus bracket minus of 9.81 into 1.5 meter. You can note down and check the calculation right now. I will tell you once again. Total stress is equal to 17.21 gamma dry multiplied by 2.5. That is the total stress. Pore pressure is negative value 9.81 into 1.5 meter.
Two and a half. Two and a half.
No, sir. No, no, 2.5.
No.
Pore
Yeah, yeah.
volume.
One and a half only. Yeah, you are right. One
It
and a
is.
half only. Right. Yeah.
Yes,
Yes.
sir.
Yes.
Is it
Yes.
clear?
Yes. Yes.
That's all, sir. You can check the calculation. You will get the answer.
Then effective stress will be increased at that level.
Yeah, it will definitely increase because capillary pressure.
That's what I am telling. I am also telling the same, sir. I am also telling the same thing.
Yeah, capillary pressure
Hmm.
also called as effective pressure. It
Yeah,
will
that's
act.
what I am telling.
Yeah, but
Yeah.
the
Yes.
thing is, that won't change the total stress.
Total stress will not change, madam.
Yeah, that is what I was trying to tell. That is that
Total,
negative thing won't come inside this total stress.
Yes, madam.
total
Total.
stress will not change, but
Yeah,
effective stress will be increased.
yeah. Effective stress, that variation will come because of that change in sign actually.
Yes,
Within
Yeah,
madam.
that.
Capillary
exactly.
sign.
Yeah,
Exactly. Hmm.
that is there.
Okay.
Thank you, madam. Thank you.
Okay, thank
Thank you,
you.
madam.